Okay, I will start with the recording, and
Yes.
we start the lecture. So
Okay.
again, Natalia, very warm welcome to Muscat, where
Wow.
it is very hot, and thank you for accepting our invitation to give us a guest lecture. Actually, you are our last guest lecture for this course.
Wow.
Yeah.
Uh-huh.
And allow me, I will introduce you to the students, and then I will give the floor to you for sharing your presentation and giving us your talk.
Okay.
So our guest today is Natalia Jorquera Silva. She is a Chilean architect from the Universidad de Chile, with a PhD in architecture technology from the University of Florence, Italy. She is associate professor of the Department of Architecture in the University of Chile and Universidad de La Serena, where she coordinates the Research Center of Earthen Architecture and Heritage, CIA type. Besides, she is a director of Studio of Architecture, Arquitica.
Arquitica, yes.
Arquitica. She is specialist in vernacular and earthen architecture conservation and heritage seismic risk assessment. She teaches and conducted several research in these fields. From this, she has written many scientific articles and 2 books. At a professional level, Natalia has worked in several restoration and seismic retrofitting projects of Chilean adobe historical buildings, most of them funded by the Chilean Ministry of Public Works and the Ministry of Culture. She participated in the committee that created the first Chilean National Building Code to restore and retrofit historical adobe constructions, the NCH 3332, from 2013. Since 2010, Natalia is member of ICOMOS Chile and member of the International Scientific Committee on Earthen Architectural Heritage, ISCIA. She is expert member since 2015, and she is also member of the Proterra Iberian American Network and of the national network Proterra Chile. In 2023, very recently, Natalia Jorquera was awarded the National Manuel Moreno Prize for the College of Architects of Chile for her contribution to the recovery and enhancement of architectural heritage. An impressive biography. We are very glad to have you and to listen to you sharing with us your expertise in this field. And your talk today,
It's about seismic retrofitting.
yes, it's
Yes.
about which is
Yes,
your field of your field of expertise, and it is very good because we haven't addressed it in our course yet. So I'm sure that it's going to be a very important contribution in the knowledge given to our students. So thank you again for that, and I give you the floor for your lecture.
Okay. First of all, good afternoon to everybody. I'm very glad to share my experience with you. I've never been to Oman, so it's such a faraway country from Chile, so I'm very glad to share my experience. Yes, I have to say, first of all, that it has passed a long time since I have made a lecture in English. So maybe some words I can miss it, and I'm going to ask you for some help because I speak Spanish, Italian, and French. So I'm more used to Latin languages, but I think I can do it.
You are doing great.
So I'm going to share this lecture. that is named Seismic Retrofitting of Earthen Structures, and the case of Chilean heritage. To start the presentation, I'm going to make a little introduction about Chile, because I can imagine that you have never been to, or does anybody knows Chile?
I have never been to Chile.
Yeah, okay. So as a kind of introduction, I'm going to share with you some information about Chile. So Chile is located in the south of South America, being the southernmost country in the world, as you can see on this map. And it is a country characterized by being a very, very long narrow. It is 4,300 long kilometers. So like 4 times Italy, for example. But it's a very, very narrow country with just like an average of 200 kilometers wide. And it is limited by the Andes mountain in the east and the Pacific Ocean in the west. We are about 18 million people. And as we are so long and so narrow, we have a very difficult geography and a fragmented territory. That meant that there are some very populated places like the capital Santiago, and a lot of small rural towns that are disseminated wide along the territory. The distance between the capital Santiago and Muscat is almost 15,000 kilometers. So we are very, very far away. Another characteristic of Chile, being such a long country, Chile has many climates and environments. From the Atacama Desert in the north of Chile, that maybe is the place more similar to Oman, to the ice in the extreme south of Chile with the Patagonia. Now I'm going to show you some landscape of Chile, because then we are going to understand how these environments, these different environments, gave born to different kinds of architectures and different kinds of building technologies. So this is a pictures of Atacama Desert. That is the driest desert in the world, much more drier than the Sahara Desert. And I was here until yesterday for a week. This is Atacama Desert, and the Atacama Desert is full of archaeological sites and full of geoglyphs like this one. That is the the biggest geoglyph in the world. This is the central part of Chile. That is a part with temperate climate and full of wines, full of trees. And this is the south of Chile. And as I said before, is in the Patagonia zone that is full of ice and rain, and it's always cold. And this is the capital, Santiago, that you can see is a very modern capital with a lot of very high towers and made of iron, concrete, and so on. So the capital, Santiago, is very if you are recording now. Yes, okay, so recording in progress. Okay, it's okay. Yes, I was telling that this is the capital, Santiago, that as you can see is a very, very modern capital with a lot of very tall towers, very modern one. And the tallest towers of South America are in Chile, although we are a very seismic country, because we have very good engineers, seismic engineers. So I just wanted to show this to make you see the contrast between the modernity of this capital and the rural and vernacular settlements that Chile is full of. then I was saying that due to these very different climates and environments, traditional and vernacular architecture is very, very different from the north to the south of the country. Because as in all the rest of the world, until the 20th century, architecture was made of natural available resources. So in the north of Chile, that is the part where I work and where I live, vernacular architecture is made of raw earth and stone, as they are the only natural available resources, because we are in the desert, in the hot part of the country. In the central part, traditional vernacular architecture is made of adobe walls and wooden structures, as there are more trees, because climate is more temperate and sometimes it rains. And instead, in the south of Chile, where it always rains and is full of forests, vernacular architecture is entirely made of wood. All the examples I'm going to show you today are those one of the northern part, as I work there and I live there, and because it is, I think, more similar to your architecture. And I have to say a very important thing. In the north of Chile, where I work and where I live, there's a lot of indigenous population still until today. So some traditional features and a lot of cultural heritage is still alive. Instead, in the central and in the southern parts of Chile, most of Chileans are a mix between Spanish conquistador and indigenous people. Yeah, I think it's an important thing. Now I'm going to talk about the seismic hazard that is the focus of this lecture. So Chile is considered the most seismic country in the world, much more than Japan, I have to say. Although if Japan is maybe more famous than Chile, because we have on average an earthquake about 8 magnitude degrees every 10 years, more or less. Yeah, so we have a very, very frequent earthquake of very high magnitude. This is due because of the subduction zone between the Nazca Plate that is here in the Pacific Ocean that introduced under the South American plate where Chile and Peru is located. So this area is named the Pacific Ring and is considered the most where the seismic hazard is more dangerous. So from 1570, so from where the Spanish arrived to South America and to Chile, and they started to write every earthquake, because before the Spanish we didn't have writing. More than 100 earthquakes, about 8 magnitude degrees, are recorded. And the highest and strongest earthquake in all the history was in Chile in 1965. It was on Valdivia earthquake in the south of Chile, and it was 9.5 magnitude. So it is considered the strongest earthquake in the world. And you can see on the left that although the architecture was made of entire wood, so inelastic structures, it was all very, very damaged with this deformation of the structures. And all the geography of the south of Chile changed with this very, very big earthquake. This is one of the most recent earthquake that it was a very, very big earthquake. It is considered the third strongest earthquake in the world the last years. That it was the earthquake of 2010, so 14 years ago. It was also in the south of Chile, and as you can see on the right, a new concrete tower was completed falling down, and a lot of people died on that towers. So just to show you the hazard. These are all the registered earthquake that has hit the capital Santiago since 1575. You can see they are like 15 earthquake of magnitude over 7. And you have to consider that between one grade and the other, there's exponential, how to say, like between, for example, 5 and 6 magnitude, there are 10 times this. I think I can explain, no? 10 times more stronger. I don't know how to explain. And so, of course, all these frequent earthquakes have conditioned the characteristic of the architecture, as you can imagine now. Elements like such as buttresses and wooden reinforcement in adobe structures and in stone structures and in masonry in general appeared after the most important earthquake in the 16th and 17th century. So in these pictures, you can see how after the biggest earthquake in history, some features of architecture changed. And very important characteristic is that because of this, all this earthquake, and also because we were a very poor colony for centuries after the Spanish invasion that was in the 16th century, because of these things, all of our architecture became very austere and with well-defined structural characteristics, such as the predominance of horizontality, low slenderness, and all the masonry architecture in Chile, as you can see in these pictures, have a few openings, a very, very walls with wide, very, very wide walls. Therefore, in Chile, we have very little monumental architecture, and traditional architecture is like you can see on this picture, that this is a picture of Santiago, of the historical center of Santiago, the capital, at the beginning of the 20th century. So you can see, for example, all this architecture of Spanish origin are just of one floor, an unique floor architecture with these wide walls, few openings, and very, very horizontality. So this is like the most important characteristic of Chilean architecture. These are some examples. I'm going to show you now some examples of historical architecture from different parts of Chile. These are the only, how to say, more monumental ones in the capital Santiago. On the upper side of the slide, you can see the government's palace. That is named La Moneda. This is a masonry building that was built in 1780. And as you can see, it's always a very, very horizontally building with slow slenderness. And these are all, this is all Justice Palace and some private houses. As you can see, this is our monumental architecture that always has this character, being very, very like fat, you know, to resist the earthquake. The vernacular architecture in places of Chile. This is the typical vernacular house from indigenous people in the northern part of Chile, in the Atacama. And as you can see, by being horizontally, few opening, and as you can see here, it is made of stone. These are the, now I'm going to show you a lot of examples of in the Andean northern part of Chile, that also you can see that they have this characteristic of being very, very horizontally fat without opening or with very few openings. So this is the Tacora Church, and it is in the northern part of Chile. It is made of ramp earth. This is another example of an Andean church, Andean vernacular church. It is made of stone and earth, always in the same part of Chile. This is another church, Amauta Church, always in the northern part. This is another very, very fat church that is named Machuca Church in the desert. Yes. I wanted to show you a lot of these churches because I have made a lot of restoration project in this part of Chile. And I think it's very, very nice to show you how churches can be so such a little and so fat and so horizontally because of the earthquake. Because in the rest of the world, churches are most of the time very, very high. So here is all the contrary. And this is the traditional architecture of the center part of Chile. This architecture of Spanish origin that is most of the time made of adobe walls with this very, very big roof and this external gallery, because this is a part where sometimes it rains, and this is the way to protect the adobe walls from the rain. Instead, in the northern part, it never rains. We don't need this roof and these galleries. Yes, this is another rural settlements. So as you can see, this is a reality very, very different from the capital, Santiago. Also in the central area of Chile is full of these very big factories, these haciendas made entire of adobe walls. And this is an area where a lot of wine is cultivated. I don't know if that's the right word. So this is a very typical kind of architecture from the center of Chile. And now I'm going to talk about the relationship between this very big seismic hazard and architecture. So the first very important thing, I think, is that earthquakes are an opportunity to observe how architecture behaves, So from the cases of bad seismic behavior, we can learn about seismic vulnerability. And in the cases of good seismic behavior, we can learn about earthquake-resistant strategies. Most of the time, and also it was like that at the beginning of my career, we just observe the cases of bad seismic behavior. So there's a lot of literature about seismic damages. But most of the time we don't observe and we don't analyze the buildings that has had good behavior. And that's a loss of opportunity because, as I said before, from the cases of good seismic behavior, we can learn about earthquake traditional resistance strategies, because we always find in heritage, in architectural heritage, also some strategies to better resist earthquake. As earthquake, as I said before, in Chile, are very, very frequent. So of course, traditional architecture has developed some strategies to better resist them. So now I'm going to show you some characteristics that conditioned the seismic performance of adobe structures. Yes, I have to say that I'm going now to concentrate on earthen structure, but specifically on adobe structures, as adobe is the most typical technique in Chilean heritage, and I think also maybe in your architecture. So the first thing we have to observe and to analyze, and it's very, very important, is the geometrical configuration of the building. Because in all the masonry structures, like stone structures, brick structures and adobe structures, geometry is very, very important. So the relationship between the dimensions and so on. Then another very, very important thing is the constructive connections. Why? Because an earthquake will always try to separate the different parts of a building. You know, an earthquake is going to separate walls, is going to separate the roof from the walls. So the most vulnerable parts of the building are the connections. So the connections between the different constructive parts are very, very important. Then in some cases, and the cases of best behavior, we find some seismic, specifically elements, constructive elements that improve the behavior, such as wooden reinforcement, for example, metal reinforcements, or the presence of buttresses. So these, for me, are the three more important elements that condition the seismic response of a building. Then there are two other very, very important factors that are the importance of frequent maintenance of the building, because most of the time, most of all in adobe structures, the presence of humidity or water coming from you know, the shower, the bathroom, make the walls more, how to say, debilitate the walls, and so they lose their structural resistance. So when an earthquake occurs, they are weaker. And another very important factor is to not alter the original structural configuration, because many times some people, to adapt their historical houses to the contemporary needs, or to transform a house in a museum, for example, they suppress a structural wall, or they make bigger window, and so on, affecting the structural behavior of the building. So I think in this slide, we can, I try to synthesize these 5 factors that for me are very, very important. So starting for the first factor, that is the geometry of the building, there are a lot of features that condition the seismic response, but I think the two more important are this one: the slenderness, that is the relationship between the width of the wall and the highness of the wall. And we have a building code that also exists in other seismic countries like Peru and like Ecuador, that says that the relationship between the width and the height of the wall has to be less than 7. So if we have a wall with, for example, 60 centimeters, the maximum height that I can have is 4 meters and 20 centimeters. You know, 60 per 7 is that. So that's a very, very important factor. And the other very important factor, if you see this plan, is the relationship between the length of the wall and also the width. And this is named the distance between braced walls. Yes. I wasn't sure if brace was the correct word in English, I have to say. Yeah? Yeah, okay. So it also said that our code said that the distance, the maximum distance between brace wall has also to be 7. So in the same example, if we have walls of 60 centimeters, we should have braced walls every 4 meters, more or less, in order to avoid a big out of plane flexion, as I show here in this picture. Another important geometric feature is that we have to prefer simple and regular plans. Like I show, this is a plan of a wine factory in the central part of Chile. But here, for example, in this plan, we can, just observing this plan, we can see which are the most vulnerable parts of the buildings. That is this one. This is a chapel in the center of the plan. And this was a very big dining room where you can see we have not division walls, brace walls. So these spaces are very vulnerable in front of perpendicular size earthquake. So this is very interesting because without visiting the building, without knowing how it is, just observing the plan, we can see where are the most vulnerable places, the spaces. Another important features in adobe masonry configuration is the adequate percentage of opening in walls. So the relationship between opening and the mass of the walls. So openings have to be little, smalls, in comparison with the mass of the walls. This is a picture of another factory in central Chile. And now I'm going to show you some example of inadequate solutions and adequate solutions to make the comparison between the features. So for example, here on the left, you have an inadequate slenderness because as you can see, this is a room that is very, very high, like 5 meters high, and is not wide. So it has a slenderness that is about 7. And how can we see what happened after an earthquake? We can see that here is like besides the shear cracks that are appearing nearby the opening, we can see that this is here is a kind of horizontal crack that is due to this too high space, you know, to the high slenderness. Here is another example of an inadequate location of an opening. An opening has never to be in the corner of the building because, as I explained before, an earthquake will always try to separate the different parts of a building, you know? So corners in a masonry building have to be always very, very good, has to have good connection. And if we put an opening just on the corner, we are not going to have a good connection. So in the pictures, for example, you can see that just this upper part of this house, we have all the responsibility to keep the corner joint during an earthquake. So of course, that's a very vulnerable part. This is another example of an inadequate location of an opening in a corner. But this is worse because we don't have just the opening of the door, but we also have diagonal walls. So we don't have one corner, but 2 corners. So we have this point and this one that are vulnerable to the earthquake because they are going to separate. And we have the opening, and we also have the roof truss here, as you can see in the configuration of the roof. And this is like, yes, I just took this picture in 2008, more or less. And I saw this house and I said, oh, this is a very vulnerable house because of this. And then after 2010 earthquake, I came back to this rural settlement and I could see that this has been damaged. So as you can see, configuration is very important because if we just analyze the plans of a building, we can prevent seismic damages because we can see which are the more vulnerable parts. Here I wanted to share with you an article I wrote some years ago, where I talked about these geometrical resistant, earthquake resistant features. So if you then, maybe I can share you, Naima, and then you can, yeah, and this is in English. So, and here I analyzed a lot of historical buildings in Santiago, comparison the different features, geometrical features of the buildings. Then, talking about the importance of the constructive connection and how they influence the seismic behavior, we have, of course, to have adequate connections, as I said before, to be better prepared to the earthquake response. Always understanding that an earthquake will try to separate the different parts of a building. And these are examples of very bad connections between division walls and the perimeter structural walls. In many cases, in historical adobe structures in central Chile, most of all, the structural perimeter walls are made of adobe masonry, but the internal division walls, as you can see in these pictures, are made of wooden structures filled with adobe. And the connection between these wooden structures and the adobe walls is very, very poor, because as you can imagine, it's not very easy to create a good connection between two different techniques. And so many times these division walls that maybe don't have a structural role because they are not sharing loads, they fall down, and it's very, very dangerous because, for example, in this example on the right, this was a damage from 2010 earthquake. Some people died here because they had here the beds, and as the earthquake was in the night, this division wall fall down, and you can imagine that this is a very, very how to say, it has a lot of weight. So although if it is not a structural wall, if this division wall fall down over your bedroom, of course, it's very, very dangerous. So it's an example of an inadequate connection. Here, instead, is an example of a good connection. This is a technique that was born in Valparaíso. Valparaíso is a city located in the center of Chile, and it is included in the World Heritage List. In Valparaíso, in the 18th century, was born this technique that is named adobillo. The adobillo, as you can see in the picture and in the drawing, is an adobe block that has in the extremes two holes. And in those holes, a little wood stick is introduced, and that stick is fixed to the wooden structures. So the problem of the bad connection between wood structure and adobe has been resolved with this technique that is very, very interesting, because I haven't much seen a technique like that, like this, in other seismic parts of the world. You know, I have been in some places with similar characteristics, like the south of Italy, south of Spain, south of Portugal, that has some very similar architecture with similar techniques, with some techniques like this with wooden structures and filling with adobe blocks. But this solution of baking this hole, I have never seen in other parts of the world. And I have shared this technique in many congresses, and everybody has always told me that they have never seen it. And here are some adobillo blocks that I received last week to test it in a laboratory in my university. So this is an example of how traditional architecture and traditional heritage has resolved some vulnerabilities. And of course, it's an example to learn from it, because as I said before, we don't have just to study the damages, but also example of good performance. This is also an example of a constructive element that was born to improve the connection, in this case, between the trusses of the roof and the beams to the adobe walls. Because as I said before, the connections between walls and between roof structure and walls is very, very important. And this is a connection that I found in the San Francisco Church that is located in Santiago. That is the most ancient church in Chile, and it has resisted many, many earthquakes, like 15 earthquakes. And I found that the church was full of these constructive elements to improve the connections. Then, talking about the third features of the architecture, in some traditional architecture, some elements to improve the seismic behavior has appeared. And this is the case of this presence of horizontal wooden reinforcements, as you can see here in the draw, that are present in the lot of adobe traditional architecture. And this is a kind of reinforcements that appeared in the 17th century after many earthquakes, and is, as you can see, a constructive element, which its role is to better connect the different parts of a building. So in this way, adobe walls that could be separated by an earthquake are better connected by this horizontal wooden reinforcement. Also, this wooden reinforcement prevent the dissemination of the shear cracks. You know the shear cracks, that those diagonal cracks that born in the corner of the openings. So if you have these horizontal elements, the dissemination of these diagonal cracks are stopped. So it's beautiful because it's a vernacular solution that appeared after many earthquakes, and it functions very well until today. So most of the time when you can see the cases of good behavior, we find this kind of horizontal wooden reinforcement. And this is it's an example of the presence of this reinforcement. And this was an analysis that I made of one of the most ancient houses in Santiago, the capital, where through the use of a thermographic camera, I could see that here, as you can see in the picture, they were this wooden reinforcement. So maybe this is the explanation why this two-floor house, that is one of the few two-floor houses, has had a good behavior until today. And this is a very interesting case that I found just 2 years ago, together with a student of mine, a master student, that made his master degree thesis about all these constructive elements, very vernacular, as you see, in a very little rural town in the region where I live, that is named Tulawen, where all the houses had this constructive element that improved the connection between beams and walls, walls and walls, roof and walls. And it was very interesting because that in his thesis of Ortega, Manuel, we found that this village has a very high seismicity. because it's on the mountain. So there was a relationship very clear between this high seismic hazard and the apparition of all these wooden elements that improve the connection. Nowadays, although because of the deterioration of this wood, of the wood, due to environmental factors, most of the wooden of this wooden reinforcement of the connection are deteriorated, so they are losing their function, and so the adobe walls are more vulnerable to suffer separation during the earthquake. So here it would be very important to replace these wooden elements with new wood. And this is a draw that is part of the thesis of my student, where you can see in blue all these wooden elements that, as you can see, improve, as you can see here, the connection between the different parts of the building with very simple solutions. And of course, where they are simple solutions, they are also economic solutions. Now, these are examples where in traditional architecture, there are also other elements that improve the seismic behavior. This is the case of the buttresses that appear most of the time in churches, where the length of the wall is too long without braced division walls. So buttresses reduce the length, the free length of the walls, avoiding the out of plane flexion. And this is an example of another church of the northern part of Chile. And here in these plans, you can see how there is a relationship between the dimension of the church and the comparison of buttresses or of lateral chapels that reduce the free length of the wall. And in this case, where there's a very little church, maybe we don't need the buttresses, or maybe just in this bottom part. But in these examples that are that are bigger, you can see how buttresses and lateral chapels appear to reduce the length of the wall, avoiding the out of plane bending. Then talking about this very important factor in all the conservation of heritage, earthen heritage, there's the prevention, most of all, of the excessive humidity. And this is an example very important, because this is part of the San Francisco convent that is also part of this San Francisco church that I showed you before. And I told you that is the oldest building in Chile. That is a building that had resisted like 15 earthquakes over magnitude 7. And as you can see here, an important part of a wall had this partial collapse because of humidity. And this humidity came from a bathroom that was in the upper part of this room. So it's incredible. You can see that a very strong building that had resisted 15 earthquakes because of a water bathroom filtration, so could have a partial collapse of the adobe wall, that as you can see here, because this partial collapse of these adobe walls produce, of course, the partial collapse of the beam of the roofs, and so an entire structural damage in all this part of the building. And as you can see, it was a very, how to say, little thing that it could have been prevented, but nobody saw it at time. And this is an example of the same thing. This is an historical house at La Serena, that is the city in the northern part of Chile where I live, where I don't know the name, the tube where the rain rains was inserted in the adobe walls, and it had an infiltration. So every time it rains, and it rains very few, this water came into the adobe walls, and someday, without 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 knowing before, the adobe walls fall down on the sidewalk. So this adobe wall had completely lost their structural resistance. So of course, this made the building more vulnerability to earthquake. And so all this deformation that you can see in the upper part of the building are because this hole in a structural wall. So this is, I think, is very important because in Chile, as we have a lot of earthquake, all conservationists, architects, and engineers are always looking at the damages from earthquake. And so most of the time, we don't see and we don't prevent the pathologies that came from humidity. And as you can see, there's a very strong relationship between humidity and the loss of the resistance of the wall, and so the loss of the structural performance. So we have to pay attention of that. And this is an example of a museum that had these important damages in the 2010 earthquake because it had the owners of this museum had changed the structural configuration of the original buildings because they transformed this historical house in a museum, and they suppressed the division walls that braced the adobe walls to make these spaces bigger in order to show the, the exposition of the museum. But as you can see in the last picture here, these adobe walls had this kind of damage that came like, I don't know how to say, like the bending inside. And so we can see here that there's no the division wall that had the. And so, which are the most typical damages in adobe structures? We can synthesize two kinds of principal damages that can be a little altered by the other characteristic I said before, like the humidity, like the the alteration of the structural configuration. But if we have the original structures, we always have these two kind of main damages. The first one is the comparison of these seismic shear cracks that I said before, that are these diagonal cracks that appear around the openings of windows and doors. And the shear cracks appears when the earthquake is in the same plane of the wall, and the stress of the earthquake exceeded the resistance of the material. So there's a relationship between the resistance of the wall and the stress introduced by the earthquake. And of course, as maybe you can know, adobe walls has very different resistances. It depends on the kind of earth, on the presence of fiber, straw fiber or not, on the main craft, on the maintenance, and so on. So the gravity of this shear crack will depend on that. And it's very, very easy to recognize this kind of shear cracks because, as you can see here on the draw, then you can see these cracks on the buildings. These cracks, when they are not repaired on time, after many earthquakes, can become very, very dangerous, as you can see on these pictures. This is named accumulated damages. It's very, very difficult that in a first earthquake, you will have a damage, a shear crack like this. But after 5, 6, or 10 earthquakes where you have not repaired adequately the damage, you can have a shear crack like that. And of course, a shear crack like this can become worse and can conduct to a partial collapse of a wall. This is very important, because, for example, in Chile, although if we have very frequent earthquake, we don't repair adequately the damages. So in every earthquake, the damages get worse, because the stress introduced by earthquake will prefer the weakest part of the wall. And the weakest part will be the crack. So a crack that in a first earthquake is just about 1 millimeter, and the second earthquake will be 2 or 3, and in the 10th earthquake will be like this. And the other typical seismic damage is this out-of-plane mechanism that is due to the poor connection between perpendicular walls and between walls and roof. That is what I said before, the importance, I talked about the importance of the connection. When we don't have good connection between walls and roof, it's very typical that when we have an earthquake in the perpendicular direction to the walls, so in this case, in this way, we are going to have this mechanism. This mechanism at the beginning, so in the first and second or third earthquake, we're going to see it like a vertical crack along all the wall. And in the next earthquake, always because of the accumulated damages, can conduct to the collapse of the wall. And these are another examples of the same mechanism in different parts of Chile, in different kinds of architecture. So this is in maybe in the third or fourth earthquake, and this is maybe in a eighth earthquake, where it's just to collapsing. And now I'm going to show you some seismic retrofitting criteria and projects. I don't know if we will make the question at the end of the lecture, or there are some questions now because of this first part of the lecture. What do you prefer?
I just inquired about that, and they told me they prefer to wait until the end of the lecture.
Okay.
So go on.
So I'm going to continue. So before talking about the criteria and to show you our building code, I have to say that until 2013, so until just 11 years ago, we didn't have a specific building code for historical retrofitting of structures. So we applied the building code for new buildings, and that meant that a lot of historical earthen buildings were reinforced with concrete, like it happened in many places in the world. And this concrete, that in earthquake, as you can see in these pictures, caused more damages to the building because of this named hammer effect. I don't know if you know this effect is that these more elastic structures of concrete, like a concrete beam, that in an earthquake is more elastic, so it moves in this way, and that those walls move much slowly, and they then finished making this like hammer. So in this example, this was a very important example in Chile because it was a very important church from the 17th century that had survived to like 10 earthquakes without reinforcement. And it was reinforcement in 1985 that in an earthquake. And because of those reinforcements, it had these damages in an earthquake in 2005. So it is very clear that it was because of this concrete reinforcement that the dome walls suffered this collapse. So this was a very important example because it made a public institution to think about it and to say, oh, we need a specific code for earthen historical building. We can't use concrete because this is a very clear example. And so in 2013, we created this building code for the intervention of earthen historical structures. We have two versions of this code. One that one from the left that was created specifically for the houses. So it was yes, created by the Ministry of Housing, and this is you can download it by free if you can see it. It's in Spanish. And this one on the right, that is more thing for monumental architecture, and this is we have to pay by this this one. They are very similar, but they have like two for different kind of architecture. And I participated in the committee that created this code. That you can imagine it was made after this 2010 earthquake that as I told you before, it was very, very strong and there was a lot of damages. And here in these codes, you can see parts like this, where without being engineering, because I'm an architect, and for architects, there's a lot of recommendation about the geometrical features. So all those relationships that I told you before of slenderness, of the dimension of the openings, and so on, are in this chapter 8 of the code. So this is very important because before calling to the engineer, architects can just read this chapter and verify that these geometrical features are present or not, are respected or not in the building. So I think it's a good it's a good thing. Yes, in this code also in the previous chapter, there's a lot of recommendation about the process of a diagnosis. So this is also very important because we can, when we affront a restoration project, there's a methodology, no? We can start by the geometrical survey, the pathological survey, and so on, before the restoration and the retrofitting project. So in this code, there's also this methodology of approach to a restoration and seismic retrofitting project. Then in the chapter 8.2, there are some methodology for the calculation of the stresses that the earthquake introduced in the historical structures. And here, this is, I think, is very important. There's also a factor that modify the response of the building according the number of earthquakes that has hit the building before. So if we have an important structural damage in precedent earthquake, we put this 1.2 factor that how to say that make the behavior get worse. It's just to introduce this concept of accumulated damage in the response of the earthquake. And there's also a factor that modifies the response of the earthquake that has a relation with the category of the building. This means that buildings, for example, like hospital and public buildings in general, so with people inside, has a factor of importance higher than a house, for example. And then this is a final part of the code that makes some recommendation about the kinds of reinforcements that we can use. And as you can see, there are not concrete reinforcement, but just make reinforcement with the same adobe walls, with buttresses, iron connections, wooden connections, and so on. And now I'm going to show you some examples of these kinds of reinforcements. I have to say before that as we have a lot of earthquake and as this code is very new because it just has 11 years, we have a lot of another kind of reinforcement that had been made in a, how to say, like in an experimental way, maybe without a scientific calculation, but made by people that had a house with damages, you know? So I wrote also some years ago together with a professor of the Universidad de Chile, also this this article that I can also share with you, but this is in Spanish, about the all the kinds of reinforcement that existed in Chile. Inside the building code and outside the building code because of this experimentation that I told you before. So then I can share you also with you, Naima, if you can share you with your student. Maybe I should translate it into English, I have to say.
No
so
worries,
I'm going to show you.
Natalia, you can send it in Spanish. I have a student who learned Spanish, so she can translate.
Okay. And so I'm going to show you these 4 kinds of most typical types of reinforcement. The structural brace and partition. Then I'm going to explain it to you, everyone. The horizontal wooden reinforcement, the external wooden structures, and the contention of walls with meshes. So the first one is this kind of reinforcements that consist of adding structural partitions in those spaces where there's no these structural partitions, and so we have 2 long walls that can suffer out of plane bending. So as I told you before, if you see this plan, you can immediately notice which are the spaces like this where we don't have these structural partitions that help to prevent the out of blending. Of course, depending the kind of architecture and the use of architecture, we cannot always add a partition wall. No, if we are in a church, for example, or in a big dining room, we cannot add a division walls in the half of the space. So in those cases, we can add some frames like this that make the same role of a division wall, but without dividing the space in 2 or 3 parts. In Chile, we make this kind of frames by calculating it in wood, but also in some cases like this, in iron or in steel frames. So this, for example, is an old adobe school that was transformed in a museum in the Atacama Desert. And our engineer calculated this big steel frame reinforcement that were added in the inner part of the museum. And it had resisted some earthquake in the last year, and it hadn't any problem. The second kind of reinforcement took the tradition of this horizontal wooden reinforcement that exists in many cases, in many houses, and so it consisted in introducing these wooden sticks in the external faces in both sides of a wall. To make this, the adobe walls, has to be excavated, drilled to introduce this wooden stick. And then the sticks are connected, as you put it in both sides of the wall, by metal bars. I'm going to show some pictures and then to better explain this. And the scope of this reinforcement is to give an unitary box behavior to the building, so the parts of the building don't separate during an earthquake. It also allowed to avoid the out-of-plane mechanism of the walls, and it reduced the shear cracks. And I very much like this kind of reinforcement because it is inspired in traditional architecture. So it's proved by the time, by the history, that it functions. So in many projects, like in this project that I made some years ago, I used this kind of reinforcement. It's the one I prefer. This is a house at La Serena where I live that had originally this wooden reinforcement. You can see because by the difference of the color of the wood. And I calculated with my engineer that it was better to introduce some new reinforcement that you can see here in the elevation, that are those the red ones. So the black ones are the originally, and the red one are the ones that we introduced. In this project, we also added some metal connection in some parts where the connection of the wooden reinforcement were weak, because the wooden sticks had a length, and sometimes the connections between these wooden sticks are weak. So we also reinforce the connection, the joints between the wooden parts by adding these metal plates. Here I'm going to show you a part of the works because in this case it was very interesting because I made the diagnosis of the project, and then I could participate in the works. So I'm going to show you here because the difficulty of this kind of reinforcement, is to excavate the adobe walls. You have to be very, very careful that in the works, because you have to make this excavation, separated in one part of the wall. Then you have to introduce the wood stick, then in another part of the wall, in order to not weaken the wall. And of course, the dimension of the wooden stick has to be calculated in order to not weaken the wall. And in this case, and in general in Chile, we have at least walls of 60 centimeters of width. And this is part of the works. That is the metal bar that connected the different part of the different sticks that are introduced in one side and other side of the wall. Yes. Then the joints between the wooden stick and the adobe walls are filled with earth. Yes, I'm going to show you again. So this is the excavation. This is the metal bar that connected the yes. Of course, these reinforcements then are covered with the earthen mortar plaster, and then so okay. And these are the reinforcement of the corner and of the joint of the different parts of this wooden sticks. And here's the metal bar that crossed all the width of the adobe walls. Here's our other pictures from the works. In this part of the adobe wall where the damages were worse, we also made like how to say this integration of new adobe blocks. And here's the reinforcement of the corners and of some joints with these metal planks. This is another kind of reinforcement. This kind of reinforcement was created in Colombia, another country from America Latina, by the Association of Civil Engineers. And it's a very similar kind of reinforcement, but it added some vertical logs, as you can see here. The process is more or less the same. You can see here's the drawing that showed the excavation of the mass of the adobe walls, then the introduction of the wooden sticks, and then in a plan the connection of the wooden stick. The difference between this kind of reinforcement and the one I showed you before, that it introduced these vertical logs in the most vulnerable parts, like corners or other parts of the world that are resisting some loads. I have to say, as you can see in this picture, that this is a more invasive type of reinforcement. I don't much very like it because I think when you build an adobe structures, we always work in the horizontality. You know, you put one row of adobe walls, then another one. So when you introduce just the horizontal reinforcement, you are like working with the same logic of the process of building. I don't know if I can explain myself. Instead, when you make this vertical excavation, you are not working with the same logic of the building. So I'm not very, I don't like it very much. And this is an example of the reinforcement of a church in Chile with this method. This is the process of the work, and this is the one. And I think it's a little very invasive. And the last kind of reinforcement is the reinforcement made of contention with meshes, meshes that can be made of different materials, like metal meshes, polymer meshes, so plastic, and cotton meshes. And now I'm going to show you the different kinds of these meshes. The role of these meshes is not to prevent serious damages of the building, but just to save lives. Because these meshes avoid the detachment of an adobe blocks, but most of the time these meshes haven't had weight. You know, they are quite light, so they don't really reinforce the building, but they just avoid, they prevent the detachment of a block. So a person can go out from the building during an earthquake, but the building then can be damaged. Yes, can be damaged. And so there are different kinds of materials. The first one is this metal one. It was also suggested by this Colombian Association of Civil Engineers before the existence of the Chilean code that I showed you before. And I also have to say that I don't really match this metal contention, but I have to say that in Latin America and also in Chile, a lot of people use this because it's much more economic. It's cheaper than the other kind of meshes, and it's also much more available in everywhere. So it's not I think the best solution in a conservation way, but it's easier to use it. And here are some examples. In the previous drawing, I show you here some example where this metal meshes is put just on the most vulnerable part of the building. So in the corners, so for example, here at the base of this tympanum, and other cases like these two ones in Chile where the metal mesh is put over all an entire adobe wall. These are two examples of churches. This is very used in churches because of the big dimensions of the churches, where most of the time the slenderness is exceeded, and also the length, the free length of the wall. These are instead the contention with polymer meshes. I preferred it because they are so light that they don't alter the original configuration of the building. Yes, and I think they are more less how to say, aggressive with the original building. And here are some examples of contention in this case in a house of the entire walls with these polymer meshes. And here are the example of a church, always in the north of Chile, where you can see these meshes goes all over the entire walls and goes over the upper part of the wall. And then they are connected to the foundation of the building. And this is the last kind of contention, not really with a mesh, but with these cotton ropes. That is, how to say, more vernacular or more artisan way of containing the adobe blocks. This is a solution that was created like maybe 5 years ago, more or less, by Peruvian engineers. And I like it very much because they created these solutions because they said that most of the time in rural settlements that are very isolated from the cities, it's not easy to get the polymeral meshes or the metal ones. People and craftsmen don't know how to use the polymeral meshes, for example. And this is a much more easy way to, in some way, to contain the adobe blocks with this very easy solution. So these are, as I said, cotton ropes that are put, as you can see in these different pictures, with a distance that make sure that not a block of adobe will fall over you, you know. So the scope is the same, is to save the people life, but after an earthquake, you have to repair the building because it will be damaged maybe. And these are an example of a lot of vernacular Andean houses that were reinforced by adding these cotton ropes. And as you can see, these cotton ropes are connected to the upper beam and also to the foundation. And as I told you before, the distance between the rows are calculated in order a block don't fall, don't get detached from the wall. And then, of course, these, like all the meshes, they are covered with earthen plaster, you know. And then yes, the corner of the rows sometimes are reinforced with plastic elements. And here's a house that is just finished with the cover, earthen cover made. And I think I like this kind of reinforcement because I think it's cheap, it's easy to do it, and it don't alter much more the natural behavior of the building. So of these four kinds of reinforcement, I prefer these two ones: the horizontally wooden reinforcement and this last one. And this is, I think it's important to say that besides the reinforcement, we also need other complementary structural repairs according to the damages a building have. So most of the time we have to repair the cracks, and if the cracks are not very how to say width, we can repair the cracks by using the injection of liquid mortar of clay. And this is a very typical solution in cases where the cracks are not very width. So it's a complementary repair of the walls, because I think before to introduce a reinforcement that is an external element, we have to be sure that the wall is well prepared to receive this reinforcement. And this is another very important kind of reparation, I think, that is the integration of new adobe blocks in those cases where there's a very big erosion, for example, of the wall in the base, for example, or where the blocks were completely separated, like in this case, because of a crack or a broken, you know. And this is the case, for example, of another project I did, always of a house, and I also followed the works after, where before to introduce the reinforcement, we made all this part of the wall, of the base of the wall, with new adobe blocks because of the capillarity, the humidity from capillarity. The adobe walls had lost a very important portion of the width. So we needed to recover that part, the original width, before introducing the reinforcement, that in this case were always this horizontally wooden reinforcement. And this is the last thing I'm going to show you. This is an entire project I made some years ago of a very monumental church that is nearby where I live, that is named Sotaki Church. That is a very interesting case because this church was had another retrofitting project some years ago, less than 10 years ago. That project consisted of adding metal meshes on the adobe walls. And after 1 year, that in the earthquake of 2015, the church had a lot of seismic damages. So it was the first time that these metal meshes didn't work. And so we started to ask why they didn't work. And I think the answer is very easy. We can't, when we are making a retrofitting or a restoration project on an architectural historical building, we don't have to repeat the recipe like when we cook. It doesn't mean that if we use metal meshes in one house, it is going to work in the same way in a church or in another kind of building. We always had to make a very deep diagnosis, and then we have to choose which is the best kind of reinforcement. So I think this project failed because the team of architect and engineer just repeat a kind of reinforcement without making a deep diagnosis. So I think that I always repeat that the only recipe is not to repeat a recipe when we when we make intervention of architectural heritage. This is another view of the building. You can see it's a very big chart respect of the dimensions of the houses around. And these are the damages after the earthquake of 2015. As you can see, besides the loss of the plaster, the metal confinement meshes were rusted and bent, completely bent, showing that it was not an appropriate reinforcement for this building. I have always thought that one of the weakness of these metal meshes is, of course, the vulnerability to be rusted because as you know, earthen plaster allows the oxygen to pass to, so the metal is exposed to rusting. So before starting this project, of course, we made a new survey of the building, a geometrical and a material survey before analyzing the damages. And I think here there was the solution and the main most important thing, that was that this church was made with a lot of different materials. As you can see in all these colors, it's a church made mainly with adobe walls, but it had some parts made of wood, but two towers yes, laterally to the adobe walls made of concrete that were not originally, that were built like 100 years ago. And also an bottom part here made with concrete blocks. So it was not an unitary building, but it had this problem of the connection of parts made of different materials, you know? So we understood that the problem of the behavior of this building came from these weak connections between these different materials, because, of course, of the hammer effect that made the concrete towers to the adobe walls. These not originally concrete towers. So here, for example, you can see this vertical crack that show the union between the adobe walls that are here, that finish here, and the concrete towers here is very that were in those. These are other kind of damages. You can see here that the concrete towers that had just 100 years were very damaged. This is also very important because the rest of the chart had like 300 years, and the other walls were not damages, but these concrete walls that had just 100 years were very damaged with this kind of shear cracks. This is a demonstration. It's very important to say that we had a lot of, how to say, engineers in the world had a lot of fiducian, I don't know how to say, on concrete. And after 100 years, a lot of heritage in all around the world is showing that it's not such a strong material as we thought that in the 20th century. And this is also the demonstration of bad connections, in this case, between the wooden tympanum and the bottom part of the adobe walls. So as you can see, it had a lot of damages after the last earthquake. Instead, that in the diagnosis I suppressed some part of the plaster, and I saw the historical adobe walls were in a perfect state without damages in the last earthquake, without shear cracks, without vertical cracks. And so the parts of the chart that were made with wooden structures like this. So after showing this, we thought, oh, the adobe walls and the wooden parts of the charts are perfect, and the newer part made of concrete are not with a lot of damages. So we proposed a project where we eliminated all the concrete parts and we conserved the adobe walls and the wooden structures, and we introduced some elements to improve the connections between the different parts of the building. That was the main concept of this retrofitting project. We said the problem is the connection of the different parts, so we are going to better connect those different parts. We're going to connect it with wood, because wood has demonstrated to be complementary to the adobe behavior. And then we proposed some other punctual intervention, like we had to incorporate confinement polymer meshes for the adobe walls. Here I have to say, although adobe walls didn't have any damage, we have to respect the building codes, and it says that we have to introduce an element to confine the adobe walls. So we choose these polymeral meshes that don't change the behavior, not the weight of the building. Then we propose to replace the two concrete towers by wooden towers that were calculated by our engineer. This is a render of how we imagine the inside of the tower. Also because we thought that to repair those damages of the concrete tower will be very, very expensive in the long time. It will always cause the hammer effect to the wall, so we just thought of eliminating it and to replace it with wood. And then these are another punctual solutions. We decided to incorporate new buttresses in some places that are indicated in red in this plan. And we also proposed to create expansion joints, I don't know if that's the name in English, between elements of different materiality. And the last thing we proposed was to incorporate some metal braces in the lower part of the roof trusses. As we, according to our analysis, we saw that these trusses generated some thrust on the upper part of the adobe walls. So by introducing this metal bar, you can contrast this the thrust. And these are some renders of the of this restoration, and this is the last slide. And here's are the references. If you can, yes, I can share with you the presentation. Then you can see this. So thank you very much for your attention.
Thank you so much. Thank you so much, Natalia, for this very interesting and very rich and dense presentation about seismic retrofitting in cases in Chile, in the vernacular architecture in Chile. It was really everything, almost everything was new to me because I didn't know the vernacular architecture in Chile. But some of the...
You had to came.
Yes, we need to exchange visits, I think. But some, and it's very interesting because some of the solutions that you spoke about, we have them here in Oman. And not only with the Adobe based walls or architecture, but also with the stone architecture. The horizontal wooden sticks are very common here. Although it's
nice.
not a country that is extremely seismic. We have some earthquakes, but not as much as in Chile or Japan or Los Angeles or some regions like this. So it's very interesting to understand also the other use of these horizontal sticks. So before, I know my students are just waiting to have their turn to ask you questions. Before opening to the questions, I just want to a little bit sum up what you presented. A very interesting introduction to, I didn't know that Santiago de Chile was the Tokyo of Latin America, but it looks pretty much like that. And it is also a seismic country. So it was very interesting to enter into acquaintance with this region and this country. Thank you very much for that. Also, you addressed important points, among which the paraseismic conditions and what are the laws or the things that as an architect, not necessarily an engineer, can observe, like the geometric relationships and the location of openings and the buttresses and all these things. Also, you address the typical damages that come out of earthquakes and not earthquakes. We all know that the enemy of earth and architecture is humidity. And indeed, in the cases you presented, a building that resisted several very important earthquakes just collapses because of water. And this is really
of a bathroom.
Yes, a leaking
it's
bathroom.
Incredible. Yes. Yes.
Also, a new thing that I learned, and I think it's unique even worldwide, not a lot of countries have a building code to retrofit heritage buildings out of earth and architecture. So really, it is extremely interesting, and I think that I will dig there to see this building code and try to adapt it here, because it's really necessary for that. And then you address some examples of possible retrofitting with polymer or what have you, meshes, or the famous horizontal sticks and the frames and the buttresses and so on. And you finished with very interesting examples of your own interventions in very several buildings, the last of which is a very beautiful church that really and also I was really amazed with this effect of hammer, and I think we will talk about this, because I have particular project where we have the structure, it's a very old building where it is earthen architecture, and it was with a wooden roof, and the wooden roof was removed in a period of its life in the 60s of the previous century, 1960s. And it was replaced by a concrete slab. And now this building needs our attention, and really you attracted my attention to this thing. So we have to think about replacing this roof. The sooner, the better, I think.
Yes, you have.
Yeah,
the same happened in Italy, you know,
and it's
San
an
Francisco
Italian
church
architect
in
who
Italy.
did that too. Yeah.
Yes.
So
had some damages because that. Yeah.
So definitely I will come back to you to follow up on these questions, and I open the floor to my students for their questions. If you have questions. I have I will just